Good afternoon. Welcome to another session in this course, Applied Optics, which is offered by NPTEL. This is week 3 of our course. We have completed 2 weeks. This is the third week. And this is a 12-week course, just to remind all of you. And every week, you all have to complete one assignment of 10 short MCQ questions. And I hope all of you have attempted the first 2 assignments. The deadline for assignment 3 is in the next week. So today we will be discussing some questions from previous year's assignment corresponding to week 3. So let us get started. Okay, before proceeding, let me share the important links for this particular course with you. So in case you are joining for the first time, this is the link to the YouTube channel where all these live problem solving sessions are live streamed. And if you have missed any of the previous live stream sessions, then you can go to this YouTube channel and watch those previous videos. So it would be a nice idea if you subscribe to it, and you will be notified every time there is a new video or new live stream coming up. So with that out of the way, let us get started with our week 3 assignment. Yeah, hello. So Kalai, you have a question? So if you have a question, feel free to ask. If not, please mute yourself. Okay, so we will begin today's session with the first question, which is a very simple question. So this week, the focus was on introducing you, all of you, to the concept of wavefront, the Huygens principle, and the concept of polarization. So the questions are also based on these topics: polarization and Huygens principle and wavefronts and stuff like that. So the first question, it's a very simple question. A wavefront is the locus of all points which are in A, increasing phase, B, decreasing phase, C, same phase, or D, random phase. So let me pull out this poll for you. So there's a poll for all of you. I have launched the poll. So everyone please take about a minute to answer this poll. So once you answer the poll, I will discuss the answer with you. Yeah, all of you please attempt it. Okay, coming back. So the correct answer, as most of you got it right, is, let me bring my pen. Here is my pen. So the correct answer is option C, same phase. So for example, we have a wave electric field given as follows. Let's say A sine kz minus omega t. Then this term, which is the argument of the sine function, is what is called as phase. Okay, and wavefront is the locus of all points where this particular phase is same. So let us say let me draw this wave for you. Let us take at time t equal to 0. So at t equal to 0, I will have a sine kz, and let me draw that out for you. So it will look something like this. So that's the sinusoid. So this is the z-axis, this is the y-axis, let us say. So my electric field is in the is oscillating in the y direction. And if I look at, let's say, a point over here, this point, and so this value will be same over here, and so on and so forth. And this distance is, what is the wavelength? Lambda. So after one wavelength, the phase will repeat itself. So that's the period. So why this happens at one wavelength? That's because k lambda, so for example, this is equal to a sine k times z plus lambda. So after lambda distance, the phase will repeat itself after one wavelength. So, and also if you find out why this happens, this is because k lambda is equal to 2 pi by lambda into lambda, which is 2 pi. And sinusoids are periodic in 2 pi. So, period of sinusoidal functions is 2 pi. So, every sine or cosine function repeats itself after 2 pi. So that's how you will be able to construct the wavefront. Okay, moving on to the next question. Let me relaunch the poll. A wave whose electric field oscillations are confined in one plane is called A, plane polarized, B, unpolarized, C, circularly polarized, and D, elliptically polarized. So please answer the poll. What is the correct option? Okay, I see one person has still not answered. Everyone, please try to answer the poll. Okay, so let me end the poll and discuss the answer. So the correct answer for this is option A, plane polarized. So, and what is the plane of polarization? So, plane of polarization is the plane which contains the electric field vector and the propagation vector. Plane containing electric field vector and the wave vector, which is also the propagation direction. So, and for example, in this example that I just drew above, the plane is YZ plane. Why? Because electric field is oscillating in the y direction and the field is propagating along z direction. So the plane of oscillations is the yz plane, and this is how my electric field is oscillating. For unpolarized light, since there is one option unpolarized, so for unpolarized light, the oscillations of electric field are in all possible directions. In all possible directions, and these oscillations are unpredictable. They are completely randomized. And how do we depict them? We depict them by drawing these electric field oscillations in various directions. This is unpolarized light. Now let us consider the general case of polarization. General case. So in the general case, we will have, let us say Ex and Ey. So Ex is E naught x sine omega t minus kz plus epsilon, epsilon being some additional initial phase. And Ey, let us take it E naught y is the amplitude, sine omega t minus kz. And let us consider this at z equal to 0. So at z equal to 0, what we have is Ex equals E naught x sine omega t plus epsilon, and Ey equals E naught y sine omega t, simply sine omega t. And my total electric field, which is a vector, is simply Ex along the I cap direction plus Ey along the j cap direction. Now, combining these, what we will get is, we will get Ex over Ey, just taking this ratio, sorry, not Ex by Ey, let me take Ex over E naught x. Okay, this is sine of omega t plus epsilon from the first equation, from this one. And if we expand this sine omega t plus epsilon, this is sine omega t cos of epsilon plus cos omega t sine of epsilon. Now we can further simplify this by substituting for sine omega t from the second equation. So sine omega t is nothing but Ey over E naught y, and this times cos epsilon plus cos omega t. Now cos omega t is nothing but square root of 1 minus sine squared omega t. And sine omega t we just found from the second equation. So we will substitute that 1 minus Ey squared over E naught y squared sine of epsilon. Okay, so far so good. Further, let us rearrange some terms. So Ex over E naught x minus Ey over E naught y cos epsilon equals square root 1 minus Ey squared over E naught y squared sine epsilon. And squaring both sides, LHS and RHS, we will get the following. So we will square both the sides to give us Ex squared over E naught x squared plus Ey squared over E naught y squared cos squared epsilon minus 2 Ex Ey over E naught x E naught y cos epsilon. This is equal to squaring the right hand side. 1 minus ey squared over e naught y squared sine squared epsilon. Okay. So further, I can rearrange this by combining these terms. So here I have this ey squared over e naught y squared cos squared epsilon, and here also I have this term ey squared over e naught y squared times sine squared epsilon. Now sine squared theta plus cos squared theta equals 1. So sine squared theta plus cos squared theta, this equals 1. So using that, I can rearrange, I can bring this term over here, combine it to give me simply ey squared over e naught y squared. So let me just rearrange it. So let me remove this term from here, combine it over here, so that will just give me ey squared over e naught y squared. And let me just shift this to the left side. And on the right hand side, we have simply sine squared epsilon. So let me bring that here. Equals sine squared epsilon. Now this is the most general form of an ellipse. This equation right here in this red box is the most general equation of an ellipse. So this is general equation of an ellipse. So now from this general case, we can actually study some simple special cases. So let us look at some special cases. So let me take the first special case. Epsilon equals 0. Let me change the color. Epsilon equals 0. That's my first special case. So this, if you put in this general equation, epsilon equal to 0, what we get is the following. This equals 0. Okay, so simplifying, this is what we get upon simplifying. Now this, if you recognize, is simply the equation of a straight line. This is nothing but equation for a straight line. So straight line meaning you have linear polarization. And the slope of this line is simply e naught y over e naught x. And if I were to draw it, let me draw it over here. This is my polarization. So this is x-axis, this is y-axis. Okay, so this was the special case for a linear polarized light. Next, let us look at the special case where epsilon is equal to pi over 2. In this, let us put it back in this general equation, epsilon equals pi by 2. So we have ex squared over e naught x squared plus ey squared over e naught y squared, and cos pi by 2 is 0, so that is third term is 0, and on the right hand side we have 1. Now this is equation of ellipse. whose major minor axes are along the x or y axis. Now, if I were to rewrite these original electric fields that I had over here, or even for the z equal to 0 condition, then what we have is Ex equals E naught x sine omega t plus epsilon, and epsilon being pi by 2. So sine pi by 2 plus epsilon is nothing but, sine pi by 2 plus omega t is nothing but cos omega t. That's my Ex. Then my Ey is E naught y sine omega t. And we need to find out what shape or what direction it moves in this ellipse. So how we will do that? Let us look at t equals 0. Now when t is equal to 0, my Ex is E naught x because cos 0 is 1, and Ey equals 0 because sine 0 is 0. So let me draw an ellipse over here first for you. So these are my axes, and here is my ellipse. This is x-axis, this is y-axis. And at t equal to 0, I'm at this point. So this extent is E naught x. Then let us look at, let us increase t. Let us go to t equals time period over by 4. So 1/4 of a time period. Now 1/4 of a time period means omega t is equal to pi over 2. In this case, Ex equals 0 because cos pi by 2 is 0, and Ey equals E naught y. So I am at this point over here. This point is E naught y. Let us increase time even more. Let us go to half of a time period. This means omega t equals pi. How I am getting this? That's because time period is 2 pi over omega. This is my definition of time period. So if you do omega times t, you get basically if I put omega t equals omega t by 2, this is omega t is nothing but 2 pi over omega and then 1 by 2. So omega is cancelling, 2 is cancelling, this gives you pi. This is what I had in purple over here. So this purple, omega t equals to pi. So this purple point, this will be where? This will be Ex equals to minus E naught x. Why? Because cos pi is minus 1 and Ey equals 0 because sine pi is 0. So this point comes up over here. So my polarization is going in the counterclockwise direction, which means that I have left elliptically polarized light. Left elliptically polarized. Okay. And if my E naught x is greater than E naught y, then my x-axis is major axis. On the contrary, if E naught x is less than E naught y, then my y-axis is major axis. And if E naught x is equal to E naught y, then I have circular polarization, circularly polarized light. And because it is going in the counterclockwise direction, it is left circularly polarized light, or LCP in short. Okay, so let us look at another case now. Let us look at epsilon equals pi. So in this case, what we have is Ex squared over E naught x squared plus Ey squared over E naught y squared plus, because I'm putting in this general equation, so cos pi is -1 and there is already a minus sign here. So that makes it plus 2 Ex Ey over E naught x E naught y equals to 0. So if I simplify, then I have Ey over E naught y plus Ex over E naught x whole squared equals 0, which implies Ey equals minus E naught y over E naught x times Ex. This is again equation for a straight line. Straight line means it is again linear polarization. And this time the slope is negative. Slope is minus E naught y over E naught x. So if I were to draw it for you, since the slope is negative, this time the oscillation would be somewhat like this, where this is x-axis, this is y-axis. Finally, let us discuss our last special case, which is for epsilon equals 3 pi by 2. In this, we get Ex squared. Again, we will put epsilon in this general equation right here. We get Ex squared over E naught x squared plus Ey squared over E naught y squared equals 1. This is again the same as the equation we got over here. This is equation of ellipse whose major minor axes are along x or y axis. But there's a difference over here. What is the difference? If I write the individual electric fields, it will be E naught, so individual electric field. So let me write it here. So it's E naught x sine omega t plus epsilon. And if I do put in epsilon equal to 3 pi by 2, this gives me minus E naught x cos omega t. Here we had plus E naught x. In this case, we had plus E naught x cos omega t. Now we have minus E naught x cos omega t. Ey remains the same. E naught y sine omega t. So let me again draw the ellipse. Let me copy this ellipse from here. And we need to figure out the handedness for this particular case. So this is my ellipse. Let me erase these. Okay, great. So again, let us look at these conditions: t equal to 0, t equal to t by 4, and t equal to t by 2. So at t equals to 0, I have Ex equals to this time minus E naught x and EY equals 0. So my point is over here. Then let us look at the next time, which is t equals, okay, I don't have much space. Let me write it here. T equals t by 4. That is omega t equals pi by 2. In this case, I have Ex equals to 0, Ey equals E naught y, same as previous case. So this point is over here. And finally, let us look at this last point for us. T equals t by 2. That means omega t equals pi. In this case, my Ex equals plus E naught x and Ey equals 0. That means I am at this point over here. So with time, this ellipse is going in the clockwise direction like this. In the clockwise direction. So clockwise direction is called right elliptically polarized. So this is right elliptically polarized light. And again, all those conditions are valid, that if E naught x is greater than E naught y, then x-axis is major axis. And if E naught x is less than E naught y, then y-axis is major axis. If E naught x is equal to E naught y, then we have circular polarization. And this time it is right circularly polarized, so it's called RCP in short. So this was a general discussion or polarization and the different types of polarization that we can have: linear, circular, or elliptical polarization. And this was the answer to the second question. The question was very simple, but I just wanted to discuss these cases of polarization with all of you so that it is clear once and for all. And anytime you want to figure out the polarization of light, this is the method that you will do. You would write the x component, the y component like this. So you will write down the x component and the y components, and then you will take different timestamps: t equal to 0, t equals to t by 4, t equals to t by 2. These different timestamps you will take, and then you will try to figure out how the electric field is going, whether it is clockwise or anti-clockwise, and then decide your handedness and the type of the polarization as well. So this is very important, and you should remember this general procedure for finding out the state of polarization instead of trying to memorize certain conditions. So I hope this is clear to all of you. If there is a question, please ask me. So it seems there are no questions. Let me check in the YouTube chat box. Okay, it seems there are no questions and we can proceed further. See, right now I've discussed this general procedure for finding the polarization, and this will be helpful to you in this next question, wherein you have to find out the state of polarization given some electric fields. So let me relaunch the poll. So this is the third question. Two waves, Ex equals E naught cos kz minus omega t and Ey equals minus E naught cos kz minus omega t overlap in space. The resultant would be A, linearly polarized, B, unpolarized, C, elliptically polarized, or D, left circularly polarized. So again, all of you, please take about a minute to answer this question using the procedure I have just described above. I see one person has still not answered. Everyone, please answer. Okay, so the correct answer is, let me stop the board. The correct answer is option A, linearly polarized. So someone has selected unpolarized. Let me repeat what unpolarized light is to make it clear. Unpolarized light means that the oscillations of the electric field is in all possible directions and it is completely random. At one instant, the electric field is along x-axis. Next second, it will be along y-axis. A third second, maybe it is at 45 degrees to the x-axis. Then maybe it becomes 30 degrees to the x-axis. Then it becomes 70 degrees to the x-axis. So it's like randomly, sometimes oscillating like this, and oscillating in all directions and completely random. That is unpolarized light. Here, we have a very fixed state of polarization. You have the electric field. So if I write the total electric field, that is simply Ex I cap plus Ey j cap. Okay. And if you take the ratio Ex over Ey, or rather the other way around, let me take it Ey over Ex, then you see this comes out to be equal to -1, which is a constant. So the direction of oscillation is a constant. And this is the equation for a straight line. This is a straight line equation for a straight line whose slope is -1. Straight line with slope equals -1. And what that line will look like. So these are my axes. And the oscillation is like this with slope. Let me redraw. With slope equals -1. Slope -1 meaning this angle right here is 45 degrees. So I hope this is clear right now. This particular case is linearly polarized light. The electric field oscillations are in a particular direction, which is like this with a slope -1 and making 135 degrees from the positive x-axis and 45 degrees from the negative x-axis. So that's the direction of polarization. So electric field will be oscillating along like this, and it will not change direction with time. This ratio Ey by Ex comes out to be independent of time. So it will not vary in time. Okay, so I hope that clarifies, and now you understand the difference between polarized light and unpolarized light. Let's proceed. This is again a very simple question. on the Huygens principle. So let me relaunch the poll. Everyone, please take about a minute to answer. So someone has a doubt? Kalai, you have a doubt? Hello? Kalai, do you have a question?
Yeah.
I'm sorry, I'm not able to understand. Could you repeat? Okay, Kalai, could you please type your question in the chat box? I'm not able to understand. And if you don't have a question, please mute yourself.
Yeah.
Kalai, if there is a question, could you please type in the chat box? Okay, fine. Let us discuss the answer. So let me stop the poll. So the correct option is option C, lesser than a rarer medium. So speed of light in a denser medium is lesser than that of the speed in a rarer medium. And simply I can discuss how this is. So C is the speed of light in vacuum. Speed of light in vacuum. And V is the speed of light in medium. And let us say we have medium 1. Medium 1, the speed will be V1. And speed of light in medium is defined as follows. V equals C over N, where N is refractive index of medium. So for medium 1, we will have V1 equals C over N1. And for medium 2, we will have V2 equals C over N2. And let us say medium 1 is my denser medium and medium 2 is my rarer medium. What this means is that N1 is greater than N2 because the refractive index of a denser medium is more than that of a rarer medium. So this means if N1 is greater than N2, then V1 will be less than V2. Okay, so from here you can easily see why speed of light in a denser medium will be less than that of a rarer medium. Okay, this was simple. And just to revise ourselves what Huygens principle is. So let me rewrite this Huygens principle for you. So Huygens principle says that, where do I have space? Okay, let me write it here. Huygens theory. What it says is that every point on a wave front is itself the source of secondary wavelets of spherical secondary wavelets. And these secondary wavelets emanating which emanate from different points they interfere, they mutually interfere. The sum of these secondary spherical wavelets, sum of these secondary spherical wavelets forms a new wavefront. So in the first few lectures of this week, you would have seen the application of this Huygens principle, how we used to study refraction and come up with Snell's law. So derivation of Snell's law from Huygens principle was quite simple, we saw, and we also came up with the laws of reflection simply by applying this Huygens principle. Okay, so that's that. And let us move on to the next question. The fifth question, again, this is a very simple question. Let me relaunch the poll. So all of you please answer. I see there is someone who has joined by the name Samsung SMS9. I think maybe that's the name of the phone or tablet from where that person has joined. So I'm sure your name is not Samsung SM or something. If you could please rename yourself, that would be very nice. Okay, so a few more seconds, then we will discuss. Okay, so let me end the poll and share the results of the poll. Let me share the results. Okay, so it seems people have selected different options. I'm still waiting for that one question which everyone gets right. I hope towards the end of this course, once all of you watch all the videos, we will be able to get to that one question which everyone gets right. For now, the correct answer of this question is, the question is, if a wave gets refracted into a denser medium, which quantity remains invariant? Invariant means that it does not change. So when a wave enters a medium, then what is that one quantity which remains unchanged? The correct answer is frequency. Frequency remains unchanged. So if this frequency is a property of the source, so if you want to change the frequency, you have to change your source itself. There is nothing else that you can do to change the frequency. Whereas speed, you can change by changing the medium. We saw speed of light in medium is c by n, c being speed of light in a vacuum and n being the refractive index of the medium. Similarly, wavelength also scales as lambda over n. So wavelength lambda naught, let me say, lambda naught being wavelength in vacuum over n. So if wavelength in vacuum is lambda naught, then in the medium it will be lambda naught over n. So you can change the speed of light, you can change the wavelength, but you cannot change the frequency. Unless and until you go back to your source and do something in your source. So that completes 5 questions. We are halfway through, 5 more questions to go. The next question is between phase difference and path difference. Let me relaunch the poll once again. So the question is, the correct relation between phase difference and path difference is A, phase difference is 2 pi by lambda times path difference. B, path difference equals 2 pi over lambda times phase difference. C, phase difference is 2 pi into path difference. Or D, path difference equals 2 pi times phase difference. So all of you have about a minute to answer. Very simple question. Okay, so let me stop the poll. So the correct answer to this question, the relation between the phase and path difference, is option A. Phase difference is 2 pi over lambda times path difference. Someone has selected option C, which is incorrect. And you can simply see why all of these options are incorrect. Why? Because all of these are dimensionally incorrect. How they are dimensionally incorrect is because Uh, phase is measured in radians. Uh, 2 pi is also in radians. And in the denominator, you have lambda, that is distance. And on the left hand side, you have path difference, which is also distance. So if I look at option B, the dimensions of option B, so we have distance means length. So we have length. This we are saying is equal to 1 over length because of lambda. But this is definitely incorrect, doesn't make sense. Similarly, C, you have on the left hand side, you have phase difference, meaning it is dimensionless. It's a constant. It doesn't have any dimension. So dimensionless is equal to, you are saying on the right hand side, we have path difference, which has dimensions of length. Again, this doesn't make sense. The dimension of length cannot be a dimensionless quantity. Similarly, for the last one, you have on the left hand side path difference, which has dimension of length. And on the right hand side, you have phase difference, which is dimensionless or dimension of radians. So all these are dimensionally incorrect, which doesn't really make sense. So this is how you can actually eliminate some of the incorrect answers in an MCQ type question. So whenever you have an MCQ question and you do not really know exactly what the correct answer is, you can try and use dimensional analysis to rule out the incorrect options. So here in this question, even if you did not know what the correct answer was, you could still find out the correct answer by this simple dimensional analysis. If instead there was one option which would say that phase difference equals, let's say, pi over lambda times path difference, then you would have a tough time deciding which option is correct, because one is 2 pi by lambda times path difference, one is saying pi by lambda times path difference. Then you would have to know what the correct answer is to select it. But for this particular case, you could simply use dimensional analysis to figure out the incorrect options and then select the correct option. So this is a neat trick that you could use in any MCQ type question. Okay, so next question. Let me relaunch the poll once again. In a homogeneous isotropic medium, polarization is associated with the direction of electric field vibration, or direction of magnetic field vibration, or direction of propagation, or none of these. So you have about a minute to answer the poll. Okay, let me end the poll now. Yeah, so the correct option is option A, the direction of electric field vibration. So polarization is associated with the direction of electric field vibration, and this is simply convention. So electromagnetic waves consist of electric field as well as magnetic field, but typically most mediums that we have are dielectric in nature and they interact strongly with electric field, whereas most materials that we have are typically non-magnetic in nature, so they do not interact that much with magnetic field. So as a result, it is the convention to use the direction of electric field vibration for polarization. So this was pretty simple. Next up, we have a question on the magnitude of electric field vector. So once again, we will relaunch this poll. So the question is, if the magnitude of the electric field vector remains constant, the wave is known as A, linearly polarized, B, circularly polarized, C, elliptically polarized, or D, none of the above. Okay, I will stop the poll now. So most of you selected the correct option. The correct option is option B, circularly polarized light. And let us discuss why this is the correct option. So magnitude of electric field is given as Ex squared plus Ey squared. This is the magnitude of electric field when you have electric field given as Ex I cap plus Ey j cap. Okay, and Ex and Ey, they are what? Ex equals E naught x sine omega t plus epsilon. We are looking at z equal to 0 right now, and Ey equals E naught y sine omega t. Now, for circular polarization, what are the conditions? For circular polarization, you have the condition that E naught x equals E naught y, and you also have epsilon equals to pi by 2 or 3 pi by 2 or such odd multiples of pi by 2 or 3 pi by 2. Okay, and in this case, my magnitude is Ex squared plus Ey squared, which is E naught. So let me call this equals E naught. So E naught x is equal to E naught. So E naught squared. And when epsilon equals pi by 2, then sine pi by 2 plus omega t is simply cos omega t. So cos squared omega t plus E naught squared sine squared omega t and sine squared theta plus cos squared theta equals to 1. So you get simply equals to E naught, which is a constant. So magnitude of electric field remains a constant for circularly polarized light. Then if we look at the case of linear polarized light, then in linear, epsilon is equal to 0 or pi or multiples of pi. And in this case, my magnitude turns out to be ex squared plus ey squared. This is equals to E naught x squared sine squared omega t plus E naught y squared cos not cos, E naught squared sine squared omega t, and we can take out sine squared omega t common. So this gives us E naught x squared plus E naught y squared sine omega t. Okay, and this you see varies in time because of the sine omega t function. This magnitude varies as a function of time. It keeps on changing with time. At t equal to 0, magnitude is 0. At t equals to, at omega t equals to pi by 2, magnitude is maximum. Again, at omega t equals pi, magnitude is 0. So it is changing sinusoidically in a sinusoid manner as a function of time. And finally, we can look at the elliptical case. So for elliptical polarization, we have epsilon equals to pi by 2 or 3 pi by 2, same as that, or odd multiples. Same condition as that for circular, except that now the amplitude E naught x and E naught y need not be equal. So now you have magnitude equals Ex squared plus Ey squared, which is equal to E naught x squared cos squared omega t. Why? Because sine omega t plus pi by 2 is cos omega t. Cos squared omega t plus E naught y squared sine squared omega t. And this is also a function of time. This varies with time. So only the circular polarization has magnitude which is constant. And if I were to draw the circular polarization for you, then the circular polarization is depicted like this. Like it's off center. Let me bring it in the center. Yeah, that's much better. So this is x-axis, this is y-axis, and the electric field goes around in a circle. It starts along x-axis. Let's say if it is at x-axis along certain time, then after some time it will rotate, and these are the electric field vector lines, and these are how the electric field will go. So it will go around in a circle. So somewhat like this, the electric field will continue oscillating either anti-clockwise or clockwise, either way. So this is how the electric field will go around, and since the radius of a circle is constant and radius is what is the magnitude, So that's why this magnitude is constant. And how you can check this is, let's say you have a linear polarizer. If you keep a linear polarizer and then if you measure the intensity output, so let me draw this diagram. Let's say you have light coming in and you have a linear polarizer, and then you have light going out, and then you have a detector. Okay, this is linear polarizer. And if you rotate this linear polarizer, it can be rotated. If you rotate it, then the intensity output at the detector will remain constant. If this intensity at the detector is constant, then you have a circularly polarized light. On the other hand, if your intensity goes like sinusoid, with it going to zero and then going to maximum, then in this case you have a linear polarization. So constant is for circular. If the intensity varies like this, then it is linear. And if the intensity varies sinusoidically, but it does not go down to zero, so this is non-zero, then you have elliptically polarized light. So this is how, using a linear polarization, you can check whether you have linear polarized light or circularly polarized light or elliptically polarized light. So I hope that is clear and we can move ahead. Okay, so 2 more questions. I will relaunch the poll. In a homogeneous isotropic medium, plane of vibration contains A, propagation vector K and electric field vector E, B, electric field vector E and magnetic field vector B, C, propagation vector K and magnetic field vector B, or all of these. All of you, please take about a minute to answer. Okay, I will end the poll now. The correct answer is option A. The plane of vibration contains propagation vector K and electric field vector E. So if I were to draw, if let's say this is my direction for E, and this is the direction for K, and let's say this is x-axis and this is y-axis. then this is my plane of vibration. Plane of vibration. So the plane of vibration in this case is the XY plane. And this is the convention. So we take the electric field vibration direction and the propagation direction. Those two vectors will define a plane because electric field is perpendicular to propagation vector. This makes 90 degrees. And they will define a plane, and that plane is known as the plane of vibration. Okay, so last question for this week 3. So I will relaunch the poll one last time for today. Phase difference between two waves of same wavelength is found double of its initial value. The path difference would become would become half, same, double, or none of these. These are the options. This is the last MCQ question for this week. So please answer. You have a few more seconds. Okay, so now let me discuss the answer. The correct answer is option C, that it becomes double. And previously we had seen in this question the expression for phase difference and path difference. So this was the expression right here between phase difference and path difference. Let me rewrite it over here. So if I represent my phase difference by delta phi, so delta phi is 2 pi over lambda times delta x, where delta x is my path difference. So we have the new phase difference, which is 2 times the old phase difference. So 2 times 2 pi over lambda times the old path difference. And this is 2 pi by lambda times 2 delta x. So this 2 delta x is my delta mu. So the new path difference is 2 times the old path difference. So I hope this is clear now. So this brings us to the end of the MCQ questions. And since we have some time left, I have planned some simple simulation computational demonstrations for all of you. So these are, so I will show some simple simulations, but let me build the background for these simulations that I have planned. So in this week, you saw what is known as the principle of superposition. We studied what is known as the principle of superposition. This is one of the this is one of the most important topics in wave theory, the principle of superposition. And what this says is that, uh, let's say this, let me rewrite my wave equation for all of you. So this is my wave equation. This is wave equation. And this is a second order. Why second order? Because you have the second order derivatives, second order homogeneous, partial because you have the partial derivatives, del by del x and del by del t, partial, and linear. So the most important term over here is linear differential equation. So let me highlight this linear. And because this is a linear equation, the principle of superposition is valid for all linear differential equations. And what this principle of superposition says is that if you have a solution psi 1, so if psi equals psi 1 is a solution, and if psi equals psi 2 is also a solution, then if you combine them, if you have psi equals some constant times psi 1 plus another constant times psi 2, so a psi 1 plus b psi 2, this is also a solution. So this is what the principle of superposition says. So if you have two solutions for a given equation, for a given linear differential equation, then any linear combination of those solutions will also be a solution. And this is very important. And some of the applications of this principle of superposition would be as follows. You would use this to study beats. Okay, beats not as in what you play with the drums or percussion instruments, but this is a different kind of beats that you hear acoustically. I will explain that. The second aspect is study of wave packets. And the third important application of this principle superposition is interference. You must have studied Young's double slit experiment in class 12. That is known as the interference effect, and that is a result of this principle of superposition. And this interference effect you would study in the next week. In fact, the upcoming few weeks are on trying to study various kinds of interference effects. So this will be discussed in detail in the next few weeks. For now, in this lecture, I want to focus on beats and wave packets. Okay, so first let me discuss what beats are. So let's say I have a wave function, a solution, a cos omega 1t, and another solution which is a cos omega 2t. Both these solutions satisfy the wave equation written over here, so they are valid solutions. So if I take the superposition of them, psi equals psi 1 plus psi 2, this will also be a solution. And if I were to rewrite it, it is a cos omega 1t plus a cos omega 2t. Let me take a common. So this is a cos omega 1t plus cos omega 2t. And we can simplify this cos omega 1t plus cos omega 2t as follows. So we have a, and the simplification would be as follows. This cos omega 1t plus cos omega 2t is equal to 2 times cos omega 1 plus omega 2 by 2t into cos omega 1 minus omega 2 by 2t. Okay, and if I were to rewrite it, so this is 2a cos omega 1 minus omega 2 by 2t times cos omega 1 plus omega 2 by 2t. And what you see is that you have these two cosine terms over here of two different frequencies. So this first one over here is the difference frequency, and this one second term is the sum, the average, the mean frequency, omega 1. So this is like mean frequency, which is omega 1 plus omega 2 over 2. And this mean frequency wave is being modulated by this low frequency cosine over here, because omega 1 minus omega 2 by 2 is lesser than omega 1 plus omega 2 by 2. So this is low frequency, and this is the modulation frequency. So this low frequency modulation is being applied to this higher frequency, which is the mean frequency oscillation. And this is known as what is called the beat frequency. Okay, so and this phenomenon is very strongly observed when you have this delta omega, where this delta omega is small. When I say small, that means delta omega is much less than omega 1, and delta omega is much smaller than omega 2 as well. So the difference between these two frequencies, when that is small, then you very prominently see this effect of the beat frequency, which means that a high frequency wave is being modulated by a lower frequency wave. Now schematically, what I mean by this is, let me draw a high frequency wave. So high frequency. So a high frequency wave, let me draw. So it would look, let's say, lot of oscillations happening like this, and a low frequency would mean very few oscillations happening or in a given time period. And when you combine them, when you take the product of these two, the high frequency being modulated by the low frequency, what you get is, let me draw the product. We create some space out here. So finally, the resultant is, what you get is, or let me draw in different colors, maybe that would be helpful. So let me change this to blue color and change this to maybe some green color. Okay, and let me now draw the product. So the product, the resultant, is going to be this high frequency wave, which will be modulated by the lower frequency wave. So let me copy this. So this low frequency is there, and this will modulate this high frequency wave. So you will take the product like this. So this modulation will happen. And what that would mean is that, let me bring my eraser. What that would mean is that your oscillations now would be confined within this envelope of the low frequency wave. So this is what your oscillations would be. So your oscillations will now be confined within this region like this. And if I draw the inverted thing here, this is the wave, this is the low frequency, and this is the high frequency within that low frequency, and this is the kind of resultant that you would get. So yeah, this is how what you will get as the final result. So final result, if I were to draw in red, that would be like this. Like this, and so on and so forth. This is your resultant. And this kind of pattern wherein the low frequency is modulating this high frequency, so you will actually see hear or see the resultant, which is also some sort of an oscillating wave, modulated oscillating wave, and you would be able to hear this modulation part. And that is what I plan to demonstrate with the help of simulations to you. So let me open Mathematica. So Mathematica is a very good programming language. I use Mathematica to uh, create many neat simulations. And let me open up my Mathematica. Yeah, I hope my Mathematica screen is visible to all of you. Okay, yeah, so this, let me run this once again and show to you what is happening. So what I'm doing is, I am taking two waves. First one is cos omega t. Second one is cos omega plus d omega t. Okay. And I am varying my d omega. So d omega goes from 0 to 0.5. So it is very small number. So you see my original frequency is 1. So I am going from 0 to 0.5 and I'm varying my this frequency difference. So this d omega is nothing but the frequency difference between these two waves. First wave is having frequency omega, second wave is having frequency omega plus d omega. Also, I am plotting this function. What is this function? This is that this low frequency modulation that I just discussed. So you see that the frequency is d omega by 2, that's 5.5 d omega, and this is nothing but the beat frequency, okay? Beat frequency or the modulation frequency that we have, and we will plot both these things. We will plot the modulation as well as the sum. So when d omega is 0, okay, so this is the case when d omega is 0, you see the value of d omega is 0 over here. When this is 0, then you see that there is no modulation. It is just the high frequency wave that is there, and that's why there is no modulation. If I increase my d omega, you see now you start seeing this modulation effect. See this very high frequency blue line, very high frequency, and this orange line is the modulation frequency. Increase further, you can see now this complete wave structure, but this beat structure is not now there. High frequency modulated by this low frequency. If I keep on increasing, then at some point you will see that this beat structure will start vanishing away if the difference starts increasing too much. See, too much difference between the two frequencies, then you do not really see that beat kind of structure anymore. So This is a very simple demonstration, and you can write this simple piece of code in Mathematica for yourself and check. If I play this as an animation, see this, as d omega increases, what happens to the resultant? I can make it a little bit slower so that you people can see what is happening. See this. Okay, let me make it really slow. Let me pause this and start from the beginning. So this is no modulation frequency, and now slowly we will start adding the modulation. See how nicely you see this modulation now. So does anyone have any question regarding this modulation? If you have some questions, please let me know. So this was the animation for this modulation. Now we can actually try to listen to these beats. So how you can listen to these beats is, let's say you have two tuning forks. One tuning fork is tuned at 440 hertz. That is why 440 here, and omega is 2 pi times nu. So this is nu is 440 and 2 pi times that makes it omega. So, okay, let me stop this animation first. And the other tuning fork, let us say we take at 441 hertz. Okay. And then we add these two waves and we want to listen and see what happens when we strike two tuning forks, one at 440, one at 441 hertz. So let me run this and I will play this for you. You will actually hear that beat sound. So do you hear that? If you can hear that, please type in the chat box, or I see there is some question. Someone is raising hand. Let me go back. I see Dell has raised hand. Okay, Dell, if you could unmute yourself and tell me your name. Yeah, Soham is saying he's able to hear it. So Dell, you have a question? Dell, could you please unmute yourself? Hi, Dell. I mean, I don't know your name. If you could tell me your name. Okay, Dell, I think I'm not able to hear you. Could you please type your question in the chat box? If you can hear me, could you please type in the chat box your question? I see your hand is raised. Okay, so anyway, coming back to this simulation. So what you hear is actually that beat frequency. And you hear, what do you hear? You hear that the amplitude of the sound is increasing and decreasing, increasing and decreasing, increasing and decreasing. That's because of this amplitude modulation that is there. Now I can play each of those individual frequencies for you. Let me simply play each of these individual frequencies. Then you will understand better what is happening. So let me individually play 440 hertz. Okay, so I will play individually 440 hertz. Let me write over here. Play this individually 440 hertz. Okay. So now here what happens in the 440 hertz. You hear a constant sound, okay, constant intensity, constant amplitude. Hear that? And if I play 441 hertz, not able to actually distinguish between the frequencies because it is too close to each other. So if I increase the frequency pretty much, let me make it 480 hertz, okay? Then you will hear the difference. See, this is a higher frequency. This 480 hertz. Compare this with 440. See, hear this lower frequency, different frequency, lower pitch note you are hearing. This is lower frequency. This is higher frequency. Okay. But if I make it 441 hertz, then that's very difficult for humans to actually distinguish such a close frequency. So you hear this and hear this. So between 440 and 441, it is very difficult to actually distinguish. But when you add these two frequencies, then you hear. So here I'm adding 440 plus 441 and I hear this. And this is simply, basically it is nothing but this you see. Here you see in this, this simulation, amplitude is increasing and then decreasing. Then again it is increasing and then it will decrease. Let me plot in a much more range of time. Okay, so you see this amplitude is increasing here, increasing to a maximum, then decreasing to absolutely zero, no sound. So that's what you hear. Increasing and then decreasing to zero sound, increasing and then decreasing to zero sound. Okay, so this was about beat frequencies. I hope it is clear to all of you now. And let me come back. I have another simulation planned for you. So let me come back. So the next simulation that I have planned for you is wave packets. Okay, so what are wave packets? This is basically as a result of what is known as wave particle duality. So wave particle duality states that electromagnetic fields also display particle-like nature and wave-like nature both, as well as particles, objects, physical objects, they also display, of course, particle-like nature, but also wave-like nature. So that's wave particle duality. And what this says is, so let's say we have a plane wave. So a plane wave is represented by this cos kx, and what this is this is like this, and this wave spreads out in space, infinite amount of space it occupies. So there is infinite spread in space. So this wave spreads out from minus infinity to plus infinity. It has infinite spread. Whereas a wave packet is denoted as superposition of some amplitude ak times cos kx, k going from initial value to final value. And this is valid because of our principle of superposition that I just defined over here. That's why it's an application of principle of superposition. So because of this superposition, we can define this wave packet. And what this wave packet looks like, so when you add these waves, it will look like somewhat like this. So this is much more localized. You see, much more localized in space. It is much more localized in space. So this wave packet is a better representation for a particle. Okay, whereas a plane wave does not really represent your particle good enough because it extends to infinity, whereas a particle will be much more localized, so you would use a wave packet to describe the nature of a particle. So again, let me show some superposition of waves to all of you in Mathematica. Okay, here I have some superposition of waves. Let me run this. So what I'm doing is I'm adding these waves cos kx times 0.1. So cos 0.1 kx, where this k takes values 1 to n, and n is the number of such cos kx modes that I'm adding. So number of modes in that superposition that I'm adding. So that is k, and sorry, that is what is n. And if I add all of them and then I'm trying to plot them, so I'm trying to plot and I'm plotting the square of the result, because mod squared of the amplitude is the intensity, so I'm interested in looking at the intensity, which is basically square of the amplitude, and this is what I will plot. So let me run this. So initially, when I'm not adding, I have just one mode, n equals to 1, so it is just a plain cosine function, simple cosine function. Then I add another wave, not much difference because these uh not so much separated. And then if I keep on adding, you see uh one more wave I have added. Then let me add 3 waves, then let me add 4 waves, 5 waves. You see, as I'm increasing the number of modes in the superposition, this wave packet is becoming more and more localized. See that? Okay, let me play the animation. See it? It's becoming more and more localized in space. So this is how you would represent a wave packet. Okay? So you keep on adding more number of modes and you will get a wave packet. Here I'm keeping the amplitude same. I could change the amplitude here as well. I could maybe say that all the higher order modes that I will add will be with decreasing amplitude. Let's say like this. And then if I see, then this kind of structure I will be able to get. See it? So you can play around with this code. You can write in Mathematica, very simple, and you can keep on changing the amplitude over here and see what you get as the resultant. A very special kind of wave packet is what is known as the Gaussian wave packet, which is widely used as a representation for this particle. So what we have in a Gaussian wave packet is we have this Gaussian profile exponential minus x squared. Of course, there will be some width. I have taken the width equals 1. And this is the plane wave mode. Why I have taken exponential, you can have a complex representation for your wave, and then finally you can take the real value to give you cosine kx. So I can have exponential I kx and then modulate that with a Gaussian exponential minus x squared and take the real part of it to give me the Gaussian wave packet. And finally, and this exponential function also I'm plotting, which is the modulation. So if I plot, this is what my result is. See this? So this is the Gaussian envelope and this is the real part of that wave function, and you see it is very much localized in space, and this is used to represent particle, the wave-like properties of a particle. So a Gaussian wave packet is one of the most important forms of wave packets. So this is all for the simulations that I had planned. Let me come back. Okay, someone is asking some question in the chat box. The state of the polarization of the following wave is, okay, I am not able to read this thing properly. Let me see. State of polarization of the wave E. Okay, so your question is, let me go back. It is related to what I had discussed earlier. So this is the most general form for the state of polarization. So what we have is, you have asked the most general kind of case. So this is my electric field, Ex plus I cap plus Ey j cap. That's what you have written. And your electric fields are, what you have taken is, you have taken the value of epsilon to be pi by 4, or rather minus pi by 4. That is what you have taken as your value of epsilon. And what this is basically, this is when you put it inside this most general equation, what you will get is that for epsilon equals to pi by 4, your state of polarization is elliptical. Okay, I hope that clarifies your question. Del, could you please unmute yourself if you want to ask this question? So if I were to draw it for you, yeah, so this is the, so Del, from what I understand is, you want to find out the state of polarization. For epsilon equals to pi by 4, it falls into this general category of being ellipse. And you can find out the handedness by using this procedure that I just stated out for you. You start at t equal to 0, then you go to t equals to t by 4, you go to t equals to t by 2, and you trace out. And what it will trace out is, it will trace out an ellipse for you. Maybe I can draw it somewhere here. Let me see, where do I have space? Yeah, here I have some space. Okay, so what I have is, let me write down. I have my Ex component is E naught X sine omega t plus epsilon, and Ey is E naught Y sine omega t, and epsilon is pi by 4, and my electric field is Ex I cap plus Ey j cap. And if I put in, then what I get is elliptical polarized light. It will be something like an elliptic, like this. And the handedness would be in the anti-clockwise direction. You can check the all of this thing by basically following the procedure and the method described in question number 2 that I had discussed. I hope you will be able to do it. Oh, so Del seems to have left. Yeah, fine. So that is all for today. Some questions from week 2 assignment were left, which I had thought I would discuss in this class, but it seems that we are already out of time. So what I will do is, maybe I will discuss those questions in the next class along with the solutions for this year's assignment. So this year you have already submitted assignment 1 and assignment 2, which would have been graded for all of you, and the solutions have also been provided for assignment 1 and assignment 2. So if you have any queries in those assignment solutions, then we would discuss those as well in the next class. So next class we will primarily focus on week 4, the upcoming week. So we will look at week 4 assignment, as well as revise some of the assignment questions from the past week. So it is always important that as you move forward, you also revise what you have done earlier. you should not forget what you had done earlier, because then that would be a problem when you try to attempt your final semester exam. So yeah, so as you move forward, you should always keep on revising what you have done previously. Maybe I can solve one of the questions from that past week. A short question, let's say. So yeah, we had these questions remaining. 4 seems to be really long. Okay, let us discuss maybe question number 9. I think this looks like a short and sweet question. Okay, so let us discuss question 9. We have about a few minutes, let us say. So this is from the past week, just to revise and keep you up, keep reminding you what we had already done. This is from a question from matrix method for ray optics. And it says that a ray travels in a homogeneous medium of refractive index 1.5. The corresponding system matrix is what we need to find out. Okay, so now what we have is, let me remind you if you have forgotten, that the transmission matrix is given as follows. It is given as 1, 0, d by n, and 1, where n is your refractive index and d is the distance traveled in that medium. Distance traveled in that refractive index medium. So what it says is it travels 10 centimeters. So our d is 10 centimeters and refractive index is 1.5, which is our n. So if I were to plug that in, 1, 0, 10 divided by 1.5 and 1. So if you do this division, 10 over 1.5, then you get 1, 0, roughly 6.67 times 1, which gives you option B is the correct answer. So as someone has rightly answered in the chat box, option B is the correct option for this particular question. And maybe I can do this question 8. This is also a short and sweet question. Nodal planes coincide with the unit planes when A, media on either side of the optical system have different refractive indices, no dependence on the refractive index of the surrounding optical system, media on either side of the optical system have the same refractive index, or none of these. So the correct option, as again someone rightly answered, is option C. Now let me remind you what these are. If unit planes are those planes when the input and output ray heights are the same. Okay, and nodal planes, that means x2 equals to x1 if x is the height of the ray, and nodal planes are those planes when the input and output ray, the angles they make with the principal axis, the ray angles are same. This means that lambda 2 equals to lambda 1. So lambda, if you remember, is refractive index times angle. Lambda is n times alpha. Do not confuse this with the wavelength. So, and a general system is represented as follows. You have lambda 2 x2 equals to m, which is the matrix of that optical system, times lambda 1 x1, and this matrix is as follows. This is the general form of the matrix. So yeah, so we have done 2 questions from the previous week. We still have to do, let's say, 1, 2, 3, and 4. So 4 of these questions are still remaining, and we definitely don't have any time left today. So we will complete this in the upcoming lectures, in the upcoming weeks, where we will also revise the assignment questions of week 1 because they have been released by the instructors. So thank you all for joining. And for those of you who maybe joined late, let me share the link to the YouTube channel once again. So that's the link to the YouTube channel, and you may want to subscribe to that channel, and see you in the next class. So next class is also on Saturday, 3 to 5 p.m. and it will be conducted next week. Okay, so thank you. Thank you all for joining. Bye-bye. See you next week. Yeah, so Kalei, do you have a question? If not, then you may leave the meeting.